All right, let's talk about something that's at the heart of every single engineering project. Whether you're building a massive chemical plant or designing a tiny microchip, keeping costs under control. If you go over budget, the whole thing can fall apart. But how do engineers actually do that? How do they estimate, plan, and track where every dollar goes? Well, that's exactly what we're going to break down today.
So it really all starts with this one question, right? Why is it so unbelievably important to get the numbers right from the very start? I mean, it seems kind of obvious, but the ripple effects of a bad estimate can be absolutely massive. A promising project can turn into a total financial disaster. And this is the exact problem that the whole field of cost engineering was created to solve.
This quote from the source material just hits the nail on the head. There's never time to do it right the first time, but there's always time to do it over. Think about that. Bad planning up front doesn't just cost you more money, it costs you time, it costs you resources, all to fix mistakes that honestly you could have seen coming. The stakes are just incredibly high.
Okay, so here's how we're going to tackle this. First, we'll look at the big picture, the project cost puzzle. Then, we're going to get really specific and calculate the true cost of an engineer's time. After that, we'll see how the project blueprint gets made, how to track performance, and finally, the most important part, how all that data helps you make smart decisions.
So let's jump into our first section, the project cost puzzle. This is really our introduction to cost engineering. You can think of it as the science of managing a project's budget. And to solve this puzzle, you have to start with the most important piece, the people who are actually doing the work.
So, to solve that puzzle, you've got to understand the real cost of your most valuable assets. And that means we have to calculate engineering man-hours. Now, here's what's so interesting. An engineer's cost to a project is way, way more than just what they get in their paycheck.
Let's just use a really simple example from our source material to see how this works. Let's say we have an engineer, and their base salary is $60,000 a year. Seems pretty straightforward, right? Well, that is just the beginning. First, we need to figure out how many hours this engineer can actually spend working on projects. A typical year has 2,080 work hours. But, people take vacations, there are holidays, people get sick. When you add up all that paid time off, maybe 25 days or so, you're left with 1,880 productive hours. And that difference between standard and productive hours, it's everything. So from there, we can get a base wage. We just take that $60,000 salary and divide it by the total annual hours, that 2,080 number. That gives us a base wage of $28.85 an hour. But hold on, we are definitely not done yet.
Right, so what about all those hours the company is paying for when the engineer isn't working? That vacation time? That cost doesn't just vanish into thin air. You have to account for it. And the way you do that is by spreading that cost across the hours they are actually working.
And this table just lays it all out perfectly. You start with that base wage, the $28.85. Then you add what we're calling a PTO adder. That's another $3.07 an hour. Then you factor in government-mandated benefits, retirement, things like that. Boom, another $2.47. All of a sudden, your engineer's true hourly cost to the project is $34.39. That's nearly 20% higher than the base wage. And if you get that 20% wrong, you could bid on a huge contract and be losing money from the second you start.
Okay, so now we get it. We understand the true cost of our labor. So let's zoom back out. It's time to build the project blueprint. This is where we take all those individual costs and combine them into a master plan that's going to guide the entire project.
And the foundation of any solid project plan is something called the Work Breakdown Structure, or WBS. It's basically a fancy way of saying you take a huge, complex project and chop it up into smaller, bite-sized pieces. So for, say, an instrument and control engineer, that could mean separating the task of designing a control panel from the task of actually ordering all the parts. Each little piece gets its own goals, and that way nothing important gets missed.
That WBS then helps you create this, the Control Account Baseline. You might also hear it called a CTR, which just stands for Cost Time Resource Plan. This document is the project's Bible, its master blueprint. If you look at it, you can see how it ties together the specific tasks, the man-hours needed for each one, and the schedule. This becomes the one single source of truth that everybody's performance is measured against.
Okay, so you've got a plan. You've got a baseline. What's next? Well, now you have to track how you're doing against that plan. This is your project's regular health check. It tells you if you're doing great or if you're maybe heading for some trouble.
And the single most important idea for tracking performance is something called earned value. You'll see it written as BCWP, which stands for
budgeted cost of work performed. All it means is the value of the work you've actually finished. So, if you plan to get $10,000 worth of work done by Friday, and you did it, your earned value is $10,000. It's a really powerful way to measure what you've truly accomplished. Now, once you have your earned value, you can calculate some really useful metrics. The first one is the Cost Performance Index, or CPI. All you do is take your earned value and divide it by how much you've actually spent. The magic number here is 1. If your CPI is 1.0 or higher, you're on or under budget. You're getting good bang for your buck. If it's below 1, you're spending too much for the work you're getting done. And the second key metric is the Schedule Performance Index, or SPI. It's a very similar idea. You take your earned value, but this time you divide it by your planned value. That's how much work you were supposed to have done by now. And again, if your SPI is 1.0 or more, you're on or even ahead of schedule. If it's less than 1, you've fallen behind.
In this graph, this is where it all comes together visually. It's called an S-curve. That top line, that's your plan. The other two lines show you your earned value and your actual costs. Just by looking at this, you can immediately see the gaps. The vertical distance between what you've earned and what you've spent, that's your cost problem. The horizontal distance between where you are and where you should be, that's your schedule problem. It makes all these numbers feel real.
Okay, let's wrap this up with the most important part. Turning all of this data into actual decisions. Because, what's the point of collecting all these numbers if you don't do anything with them?
And here's the bottom line. CPI and SPI aren't just numbers you put in a weekly report to your boss. They are early warning systems. They let you spot trouble, a cost overrun, a schedule slip, way before it turns into a 5-alarm fire. This gives you time to react, to take corrective action, and to minimize those nasty surprises down the road.
So let's quickly recap the big takeaways here. First, always calculate the true cost of your people. Second, use a work breakdown structure to get organized. Third, build that control account baseline and treat it as your master plan. Fourth, keep a constant eye on your CPI and SPI. And finally, remember the whole point is to use this data to make smart decisions, not just to fill out a report.
So I'll just leave you with this one final thought to chew on. Imagine you could perfectly estimate and track every single number, every cost, every hour, everything. What do you think is the single biggest risk left that could still derail your project? It's a good reminder that even with perfect data, some of the biggest challenges, well, they can't be measured in a spreadsheet. Thanks for tuning in.